G'day, this video is to help you understand the idea of the golden ratio. I'd probably encourage you to go and Google golden ratio just to find out lots more about it. It's actually quite a fascinating concept. But in this video, I'm just going to sort of teach you how to prove it, or at least find the value that we often use, so the ratio that we're looking at. Imagine we have a rectangle over here, length multiplied by width. Now what I'm going to do is I'm going to slice this rectangle into a square and another rectangle over here. So this one's obviously, it's no longer L for this square, it's actually W, which is here, 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 and here. So a square with length W. What I end up getting is I end up getting this rectangle over here ends up being this rectangle there, so W and L minus W. And what we're saying is, well, what we're trying to prove is that if this rectangle here is in the same dimensions as this rectangle here, then we consider this the golden ratio rectangle. So that's what I'm going to try and prove, or I'm going to find out what value I would need for these lengths to be in, this length and this width, what ratio, in order to make it the golden ratio. So I've got length and width, so I'm going to do L divided by W is equal to W divided by L minus W. The other thing I need to be aware of, or I need to know, is that this is actually equal to some sort of scale factor. Okay, as in the scale factor of L and W will be the same as W and L minus W. Very similar to other videos that I've explored. This one here is going to be half of this one here, so K would be a half, or this one here is going to be double this one over here, so that would be 2. We're actually going to find out what that value is, in this video. So at first I'm just going to look at these two sides of the equal sign here. So LW equals W over L minus W. I don't like fractions, so I'm going to multiply both sides by the bottoms here. So I'm going to get L times L minus W, and I'm going to get W squared. Then I'm just going to expand this over here. So I'm going to get L squared minus LW equals W squared. Now I'm going to somehow eliminate this L, because I don't like having two different variables in there. So this is when I'm going to go back to my scale factor. I'm going to say that L over W must equal some scale factor. It could be half or triple or whatever it is. That means that L must equal KW. And I'm going to substitute that back into my original equation over here. So instead of L squared, I'm going to have KW squared minus KW times W equals W squared. So this turns out to be K squared W squared minus KW squared minus W squared equals 0. I just drag that W squared on to that side as well. Now, where do I go? Here we are. Because W squared exists in all of these terms, I can actually divide everything by W squared, which means I'm left with K squared minus K minus 1 equals 0. And this is where the beautiful golden ratio comes in. I'm going to find the value of K. So again, I'm going to find the ratio that will give me this this golden triangle golden rectangle that works and is visually appealing and beautiful and all that sort of stuff. How do I find out what K is? Well, that's simply a quadratic here. So I can do lots of different things with a quadratic, solving the equation. I can find a common factor. There is none. I can use the cross method. That's going to be tricky. I can use the completing the square. That's always going to work. Or I could use the quadratic formula. I think I'm going to use the quadratic formula because I think it jumps straight to solutions really nicely. So I'm going to say that K equals, I know that the quadratic formula is usually x equals negative b plus or minus the square root of b squared minus 4ac over 2a. But in this case, I don't have x. Sorry, I should also put ax squared plus bx plus c. But I don't have x, I've actually got k. Notice how there's no x's over this side. There's only numbers, only these numbers at the front. Okay, so I'm going to do the same thing over here, except I'm going to call it k instead of x. And just before I do, a is going to be 1, b is going to be negative 1, and c is going to be negative 1 as well. So I get negative 1 plus minus the square root of negative 1 squared minus 4 times 1 times negative 1. All over 2 times 1. Tidying this up a little bit, I get positive 1 plus or minus the square root of 1 plus 4 all over 2. The plus is because of the two negatives. And so I get k is equal to 1 plus or minus the square root of 5 over 2. Now, remembering that k is actually a ratio, and while this is true, this will make that equation true up there, you can't actually get this negative value because 1 minus the square root of 5 over 2 is actually less than 0, because the square root of 5 is roughly 2. It's a bit more than 2 actually. 1 minus 2 will be less than 0. So that one means that I can't use this value. It's not because I'm dealing with lengths and ratios and angles, sorry, not angles, sizes, a negative scale factor is actually going to be not appropriate for here. So I've simply got k equals 1 plus root 5 over 2. And this, my friends, is the golden ratio. If you put that on your calculator, I think you get something like 1.628 or something. This is the ratio that says if you have, I'll jump up here, if this length compared to this length is 1.628 or whatever it is, the golden ratio, it's referred to as a very special rectangle. It's very beautiful and it is very nice, and I'd encourage you to go and go and Google it and find out a little bit more about it. So I hope that's helped you to understand what the golden ratio is and maybe how to apply it as well. So thanks.